Okay, and now we continue on with 5.2, the energy conversion. And we are on page 96 on the conservation of energy. In here, conservation means that something that will be conserved, meaning that it will be staying within that system. It will not go away. It will stay there. That's a conservation. It will remain there. So what is the conservation of energy? Let's take a look. Now in here, actually conservation of energy actually is one of the second law of thermodynamics. And later on you will learn about this, and there are a lot more calculation you need to do in the senior forms. But right now we are just talking about what is this idea. Now in here, a ball is falling down and it bounces off the ground. Okay, so in here we start a release point, and what happened when you release it after it bounces back? Do you see that it cannot reach the same height as the starting point? You see that it will be a bit lower. So what happened? So there's a proposal saying that, okay, I think the ball has less energy than before because some energy is destroyed during the bounce. Is it true? Is it correct? Let's take a look. So in here, there's an idea of the energy can be converted from one form to another. So it can be changing from, for example, what we have seen before, from the chemical energy to electrical energy. But it cannot be created nor destroyed. So in here, energy itself cannot create itself. So it has to start somewhere, and then it will be converted into other forms. And also it cannot be destroyed. It will remain the same. So that's why we call that the law of conservation of energy here. Okay, so let's take a look at the simulation here. So in here, let's take a look. So the person over there has the highest potential energy. So let's see the person. If we increase the mass of that person, you see it become bigger and the potential energy increase. So what happens if I decrease the mass? You see that person have a smaller mass and the potential energy would decrease. Okay, so let's start from there, and you will see that when it's sliding downward, so in here you see that the kinetic energy start to pick up when the person is moving. When the person reach the bottom, so you see here the person is at the bottom and the kinetic energy is in the full extent, but the potential energy would be 0 because all of it have been converted. Now let's take a look at a different design. For example, if this person is going up, so let's take a look. Start with a lot of kinetic energy, and then when it reaches the top, when the person reached the top, you see that he has reached the full potential. All the energy from kinetic energy would be converted into potential energy at the top there. So in here, if we switch it to a U shape, and let's see what will happen. So you see that start from the full potential energy, convert into full kinetic energy, back to potential energy again. Okay, so in here, this person will keep on sliding back and forth, but eventually he will stop because of friction. But now in here, so you see that, so at the very top there, that he would have the full potential energy. When he reached the bottom, he would have the full kinetic energy, and so on. Okay, So in here, if we change the mass, it will just increase that person when he's having more kinetic energy or more potential energy. Okay, so let's switch back to our PowerPoint. So in here, there is a demonstration of what is the meaning of conservation of energy. Now in here, when the ball bounces, it will convert the potential into kinetic. And in here, it will generate the sound energy and the thermal energy. Because the ball is rubbing against the floor, it will generate some form of thermal energy, so the heat, and then it will bounce back. Okay, so that's why in here you see that it will have less kinetic energy. That's the reason why in here the ball cannot reach the same height. Okay, so in here you see that it has less kinetic energy. The energy is being converted into sound and heat energy here, thermal energy. So that's why in here, when the kinetic energy is converted back to potential energy. Now, in here, the law of conservation of energy, the energy cannot be created nor destroyed. So in here is important for you to know that, okay, cannot be created nor destroyed. And the next part, the Sankey diagram here, okay, and this is written and draw representation of what the energy would be going through in the transformation. So let's take a look at the drawing part. Okay. Now in here, we're looking at an example of a light bulb. It's 100 joules, and only 10 joules is converted into light, but the remaining 90 joules is converted into heat energy. So when you touch the light bulb, it's really hot. So the input is 100, okay, 100 joules, and output is only 10 joules light and 90 joules thermal. Okay, so let's put it into a drawing. So in here, every one of these square, if you draw it as 10 representing 10 joules, you will need 10 of them to give you 100 joules, right? 10 times 10 is 100. So in here, the output of the light energy is only 10 joules. That's the output, which is only 1 square wide. But what happened to the rest? It would turn into 9 square, because it has 90 joules would be turned into thermal energy. Okay, so here's the output, 10 joules as the light, and then the other 90 joules would be the thermal. Okay, so in here, that is the drawing of what the Sankey diagram looks like. And in here, you see the output energy and the input energy, how they can be different represented. So in here, you can look at it and say, oh, 10% would be the actual light energy coming out of it. The other 90% would be gone as the thermal energy. And in here, that's how we're going to understand the conservation of energy in this conversion process. Now let's take a look at the exercise you will need to try it. Okay, so in here, if you flip the page to the next page, you will see the projector. The input is 100 again, and the light is 10, and the other 90 joules would be the thermal energy. So how would you draw that? So it will be the same as the diagram you have done in the last page, as you have seen the demonstration. Each square representing 10 joules. That's why the output energy of the light energy is only 1 square wide. The other 9 square would be going downward to the thermal energy. And if you take a look at the next example, we have 100 joules. So we're going to draw 10 squares as the input. And for the output, we got 3 different things. So you have to be careful. So in here, what is the desired outcome of the hair dryer? Is the thermal energy. That's what we really want. So that one would be 5 squares. And the kinetic energy and the sign energy, those would be the waves. So if you take a look at it, the 10 squares going in, 5 of them would become the thermal energy. That's what you want. But the other ones, the 10 and 40, would be going downward. Those would be the waste energy. Okay, so please try this and draw it out, see you actually understand it, because it will be helpful for you to actually have a hand-on experience and actually do this. Okay, and from that we come to our key point. It's a proportional representation of what the energy going in and coming out will look like. In the checkpoint 5.3, in here the first one, the energy can be converted from one form into another. Is it true or false? Yes, true. That is the conservation of energy. We'll talk about next, but it can convert from one to another. And the energy can be created in a power station. Can energy be created? That is the question. No, it cannot. Because in here, in the conservation of energy, we're converting one form to another. So in the power station, what is happening? What is the input energy? It could be the potential energy. It could be the fossil fuel. It could be all different kinds of input. The output is the desired output of electrical energy, but that is a conversion. There is the energy, the electrical energy is not created. It is only converted. So in here, let's take a look at this diagram. So each of the smaller square is representing 10 joules. And the question here is, what is the kinetic energy? So let's take a look at this one in the diagram. How many squares is in here? There are 3 squares here. That's why in here, this will become 30 joules. And how about the next question? Oh, the next part is, oh, it's skip the, they skipped that. I'm not sure why they would do that. There's something wrong with the PowerPoint. Okay, let me show the B and C first then. Okay, in B here, there's a thermal energy. So if you go back to your textbook, count how many squares is that? That is 5 squares in width. Oh, sorry, it's 6 squares in width. That's why it's 60. And then the last one is only 1 square. That is 10 joules. Okay. And in here again, energy we are measuring in terms of joules. Please make sure you remember that. Now, in here, there's something really interesting going on in the universe, and doesn't matter what or how you look at it, in the whole universe, the energies are being converted from one form to another. Okay, so in here, that's really interesting. Is something that you haven't seen before, and that is called dark matters. And I just want to touch on this topic because it's one of the ideas that is quite interesting. Because we all assume that everything we see, those are matters, but there are dark matters, and those matters you cannot see. But actually, for every one single atom, there are 5 dark matter atoms behind it. So basically, you only see one, but where's the rest of it? Is something that you cannot see, you cannot touch, but by calculations, we can show that in the whole universe, there are a lot of this guy, the dark matters. But in mathematics, and we are starting to see that actually it's all around us, but we are not sure how it works yet, and I'm pretty sure some of you will figure out what those are. And that is a different topic. Well, for Form 1, it will be a little bit too difficult to understand what is a dark matter. It's something that we don't see it, but yes, we know it's there. Actually, we can measure the mass of it already. And those would come a little bit more difficult in terms of this topic. And if we have time, we can have discussion after you return to class, and I'll talk to you more about this. And yes, those videos we can watch it, but right now those videos would be really difficult to explain to you at this second. And let's go back to our PowerPoint for now. Okay, so in here we talk about the efficiency of the energy conversion. In here, in terms of physics, efficiency is a key to everything. If you can achieve 100% efficiency, you have a perfect system, which is impossible at this minute, but it's one of the ideas that people are trying to achieve, having higher and higher efficiency. It's the same as the solar panels. Why is solar panel so popular now? Is comparing to the 20-30 years ago, solar panel is so low in efficiency. But right now we are getting to a point that it's more reasonable. It can convert more light and will give you more energy. We are all talking about efficiency here. Now in here, some examples of the appliances at home, the fan, the lamp, they're all energy converter. From electricity change into other forms. Kinetic energy for the fan, or the light energy for the lamp. So in here you see that for electricity to go into the fan, it will turn the motor inside the fan to cause the blades to move in as a kinetic energy, and then the motor would get heat up really fast, and then it would give out the heat energy, the thermal energy. So in here, that's why the kinetic energy is something that we want. So in here, we're measuring in terms of something that we want, the desired outcome. So for the lamp itself, the electricity, it will be converted into light energy and also the thermal energy. And so in here, we're trying to figure out what is desirable outcome on, and something else is being generated, the thermal energy. In here, the thermal energy is the form of energy that we don't want. It's not something we want. When you are reading a book with the lamps shining on it, you don't want to feel hotter and hotter. That's something that you don't want. Maybe during the winter time, but during the summertime, you don't want that to happen. Even for the fan itself, you don't want the heat energy to be generated by the motor. So that's something that you don't want. So in here, that's why the concept of efficiency is really important. And you see this equation, the efficiency is equal to the useful energy output over the total energy output times 100%. Times 100% is just give you a percentage. But in here, you need to look at something that you want, that's a useful energy output. What's something that you want as output on top, and the total is at the bottom. So that's why it's a percentage, right? So how much energy is being converted to something you want, and we call that efficiency. So in here, let's take a look at an example of a fan. We have an input of 50 joules, and it's converted into 30 joules of kinetic energy, and then 20 joules as the thermal energy. So in terms of solution, it's 30 over 50 because the input is 50, and the desired output, the kinetic energy of the fan moving, is 30 joules. It's 30 over 50 and times 100% to give you 60%. So in here, the fan is around 60% efficiency. It's not really effective. Think of it this way: the fan is turning, you're wasting half the energy in terms of the heat energy. Do you want that in your fan at home? Now in here, we're comparing the efficiency of two energy converters, namely the light bulb and the CFL lamp, fluorescent lamps. Okay, so in here the light bulb, the old design, you see the filament there, and it's only 10% efficiency. If you look at it, it's 10 joules, that's as outcome, but you need to put in 100 joules for it to work. Where does the 90 joules go? It's wasted as the thermal energy. It's wasted as heat. That's why when you have this kind of light bulb, do not touch it. It's extremely hot. And comparing the fluorescent ones, and most of the light bulbs in Hong Kong now are replaced with this one, the CFL design. And in here you see, if you put in 100 joules as an input, you will get 75 joules as the light energy output, and the other 25 joules would be wasted. So in here you have to work out the efficiency. Let's take a look. So in here we got the light bulb, we only got 10 out of 100 would be useful light energy, so that's why we are only getting 10% efficiency. Compare that to I have to try this again. There's a second part to it. For some reason it's not showing it. And the second part is actually the other one, the efficiency of the CFL. So in here the other one is, you have to write it down, is 75 over 100, because in here, let's take a look at this diagram. In here is 100, but only 75 of them are so in here it is 75 over 100, and for some reason it's not working. So okay, I have to just tell you that. Okay, so in here is 75 over 100 times 100%, it will give you a 75% efficiency. So compared to the old one of 10% with the light bulb to the new one of 75% efficiency, the second one is a lot more efficient. So in here, the CFL one have a higher efficiency. Okay, so in here, that comes to the end of the second part of the calculations. In our next lesson, we will talk about 5.3, the heat transfer.